Alright, so we're gonna start derivatives today. Derivatives are really cool. I think limits are boring, derivatives are less boring, integrals are pretty exciting. So we're getting more and more to the fun stuff of calculus and what it's all about. Limits, they're fundamental, but they're pretty self-explanatory, and they're also kind of formal and boring, and yeah, whatever. But derivatives are pretty neat. So derivatives. And my first derivative video I took down because I wanted to do another series, start over. But I feel like that video was actually pretty good at explaining it, and I don't know if I'm ever going to explain a derivative as well as that again. But let's see. So we know in 8th grade or 9th grade, or the first time you took an Algebra 1 course, you learned about slope. And that's what derivative is. It's informally the slope of a function. And in algebra, you only dealt with linear functions, in algebra 1 at least, so you only calculate the slope of linear functions. And that's fine, and if it was a curvy function, you used an approximation for a derivative, that's cool too. But in calculus, what we're going to do is we're going to calculate the exact slope of the curve of curvy curve functions, curves that aren't linear, which is cool, which is the cool part. So how do we formulate this definition of a derivative in our head? How do we get there? So to do that, I'm going to draw another graph, because visual learning is, I think it's the best learning. So I'm going to make it pretty big. We're going to draw our favorite function again, which is x squared. If it's not, don't shoot me. This is, oh yeah, f of x equals x squared. This is x, this is y. Let's call this x naught. This is 0 that I'm putting on the bottom just means that it's some arbitrary value of x, and it's read x naught, or x0, but I like to call it x naught because it sounds cooler. And at this point, I'm going to call x naught plus h. And why do I call it x naught plus h? Because I'm going to call this distance here h. This distance is h. And so let me ask you something. What is the corresponding y value of x naught? And what's the corresponding y value of x naught plus h? Alright, well, let's take our cyan lines and let's draw them, connect them to the y-axis, and see what we get. Well, we don't have an explicit y value, but we can say that this is f of x naught, and we can say that this is f of x naught plus h, right? So I hope you should understand what's going on here. I'm just labeling f of x equals x squared. I'm labeling x naught plus h, and then I just labeled this graph. Well, technically the y value is x naught squared and x naught plus h squared, but let's just call it f of x naught plus h because it's simple, and I'll tell you why. So what are the coordinates for these red dots that I created here? What are the coordinates of this? Well, that's going to be x naught, comma, f of x naught. And this is going to be x naught plus h, comma, f of x naught plus h. Yes, I know that's pretty long, but you know, it makes sense. You know, this is just straight plugging in x and y coordinates. And so we can make this line that goes between these 2 points, and you can see that it's not the exact tangent. There's still a bit of blue underneath that purple line, that purple/pink line. So it's not an exact slope at whatever point may be between this x naught and x naught plus h, but it's something that we call a secant line. So let me try and slant write that, secant. So how do we calculate the secant line? Well, you know, your traditional slope is equal to delta y over delta x, or rise over run, you know, basic 8th grade, 9th grade stuff. So the slope of this secant line, so slope of secant, is going to be, well, you can use y1 minus y2 over x1 minus x2, or y2 minus y1 over x2 minus x1. I'll use y2 first. So it's going to be y2 minus y1, so that's f of x naught plus h minus y1, which is f of x naught. You with me there? This is y2, this is y2, that's y1, this is x2, this is x1, right? And this is over x naught plus h minus x naught. That's x2, that's x1. And you see here that the x naughts in the denominator cancel out. So the slope of the secant line is going to be f of x naught plus h minus f of x naught over h. And this is what we call average rate of change. Average rate of change, because it's the secant line. It's not the exact slope, but it's a good approximation. And this very, 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 very important value here is super duper important. It's what we call the difference quotient. The difference quotient. This is colorful. I like it. I like doing videos like these because it's very colorful and visual and stuff like that. So yeah, this is average rate of change. So here's a question that ties it all together. This is where the intuition comes from. How do you think we can manipulate the secant line so that the slope becomes closer and closer to the actual slope at x naught? So I'm going to estimate what the tangent line of... Oh god, I don't have the line tool. I'm going to estimate what x naught, the slope of x naught actually looks like. And I'm going to say this is the tangent line. How do we manipulate the secant so that it becomes the tangent using this difference quotient? How do we do that? Well, if you were thinking that we shrink h, if we let h go closer and closer and closer to 0, the secant line gets closer and closer and closer as this red dot moves here, and then it moves here, and then it moves here, and then it moves here, and the secant line gets lower and lower and lower and lower. The secant line moves closer and closer until the x naught plus h, until h becomes 0. And now we're just calculating x naught to x naught. But that's just the same point. So it's going to be the tangent line. So we can't actually do 0 because then we get a denominator that's undefined. What do? We use limits. So we find the limit of the difference quotient as h approaches 0. So instantaneous rate of change, instantaneous rate of change, aka the derivative, or the actual slope, equals the limit as h approaches 0 of this difference quotient, f of x naught plus h minus f of x naught over h. And since x naught is a constant, we can take the naughts out. We can use not naughts, but we can use just x, because this now goes for all x and not just one arbitrary value of x. So this is super duper important, and this is the derivative. It's the formal definition of the derivative.